Hello, my name is Yubo Fu, and today I will be talking to you about magnetic field of a bar magnet, which is Physics 2212 Lab 3. Introduction and purpose. Magnets produce a non-uniform magnetic field, and we can predict the strength of these magnetic fields using physics equations derived from the Biot-Savart law. In this lab, we will measure the distance dependence of the magnetic field due to a small bar magnet and compare those measurements to predictions that we've made using our physics model. And our experimental mu that we determined from our experiment was 0.652 joules per Tesla. Experimental setup. We first calibrate our phone's magnetometer app and align it with magnetic north to zero out the sensor so we don't see an exponent. And then we determine where the magnetometer sensor is by moving it around and seeing wherever the magnetic field is the strongest, which means that the sensor is closest to the magnetic field. And then after we know where it is, we just take measurements at the given magnetic field strength and see how far we are away from the magnet. Data and calculations. So here are the magnetometer readings and the graph that we have from the averages of the magnetometer readings. From our graph, we know that n is equal to negative 3.6472, which is the slope of the graph, and then we find that k is equal to e to the negative 15.85, which comes from taking the natural log of the intercept of the graph. And we know that the magnetic field is equal to k r to the n, or mu naught over 4 pi times 2 dipole moment over r cubed, and so we can use that to calculate our magnetic dipole moment, which would be 0.652 joules per Tesla. Coding. So the central part of this lab's code is just a function that calculates the strength of the magnetic field at a certain point due to the magnet, and we later call on this in the code to draw each of our arrows, and then we output the strength of our arrows in both visual and text form. Discussion. So now we have our data and our computational model, we can start comparing the values. So we got a value of 8.64 times 10 to the negative 6, 2.59 times 10 to the negative 5, and 0 Teslas from our computational model, and 1.2 times 10 to the negative 5, 5.95 times 10 to the negative 5, and negative 3.71 times 10 to the negative 5 Teslas for our experimental values from the magnetic field. And so this gives us a present error about 90%. So some of these errors could have been caused by the fact that the magnet was cylindrical, which made it prone to rolling around, and we had to reset it to its original location. Furthermore, the method that we find the phone's magnetometer location may have not been perfect. There was definitely a lot of ways that could have had error because we had to just find the location of the magnetometer empirically instead of just knowing where it is. And then we might have not been perfectly aligned with Earth's magnetic field. While we did our best to zero out the X component, it may have not been done perfectly. And finally, a smartphone's magnetometer is designed for getting a vague idea of which direction you're pointing. It's not a precision instrument, so that would have further added to our error just because how inaccurate the magnetometer is in general. The lab gave us 4 statements to pick which ones were true, and the ones that are crossed out are the ones that we believe to be untrue. If we hadn't oriented our experiment to compensate for magnetic north, we would have added an offset to our readings for the magnetic field from the magnet, which we would have to subtract out and adds an extra step that could cause more as another source of error. If we stuck two identical magnets together, we would expect the magnetic dipole to be about doubled, and all of our measurements of the magnetic field should be 2 times of that of just one magnet. Conclusion. We took magnetic field readings from a bar magnet and used that to calculate the magnetic dipole moment using our equations derived from the Biot-Savart law. And this gives an understanding of the distance dependence of the magnetic field. And if you wish to review the results again, they are down below on the screen.